everyone, Dr. Tullis here once again, ready to wrap up our lessons in thermodynamics with our last video lesson with a little bit of work left to do. Let's take a look at an example of a problem applying Gibbs's free energy and solving for actually the temperature at which the reaction becomes spontaneous or not. So to calculate the temperature at which the spontaneity changes from spontaneous to non-spontaneous or vice versa, we assume that the delta G becomes a value of 0, and that's defined as the state of equilibrium. And again, I'm going to emphasize equilibrium is coming to us over and over and over again in the next 3 chapters. But equilibrium is defined as saying that the rate of the forward direction is the same as the rate of the reverse reaction. So, equilibrium. The rate of the forward reaction is equal that's the equilibrium. If A and B are a dynamic equilibrium as C and D, we have the forward rate and the reverse rate are happening at the same time. So therefore, delta G is assigned 0. We know if delta G is 0, then we can say that 0 is equal to enthalpy minus temperature times entropy. We can then rearrange this equation, so let's add T delta S to both sides, plus T delta S. We're then left with only delta H on one side is equal to T delta S, and we can get T by itself by dividing both sides by entropy. So T is equal to enthalpy divided by entropy, as we see right here. So again, temperature at which delta G is 0, by definition, the system is in equilibrium. Let's look at an example here, looking at equilibrium temperature for a phase transition. So as defined in the chapter on liquids and solids, the boiling point of a liquid is the temperature at which its liquid and gaseous phases are in equilibrium. That is, when vaporization and condensation occur at equal rates. Use this information in Appendix G, and we wrote down what's in your appendix, the thermodynamic values, to estimate the boiling point of water. So we have liquid water in dynamic equilibrium with gaseous water. So that's telling us that we have liquid water turning into gaseous water and gaseous water turning into liquid water at the same rate in equilibrium. Okay, so when delta G is equal to 0, so we know that 0 is equal to delta H minus Ts, and we rearrange that equation to solve for temperature. So we're going to do delta H, or the enthalpy, over or divided by delta S, the entropy. So when we set this up, let's move this down here, we need to find delta H. All right, so delta H for the reaction is equal to the products minus the reactants. Here's our products. So we have negative 241.82. This is kilojoules per mole. Products minus reactants. The reactant is negative 286.83. So if we get our calculator out and do negative 241.82 minus a negative 286.83, we get 45.01 kilojoules, which is a positive value. So this is an endothermic reaction. And if we think about it, going from a liquid to a gas in the forward direction, that's absorbing heat energy, right? So this is endothermic, okay? So we have our delta H. Now we need to find our delta S. Okay, so again, we're going to do products minus reactants. We have 188.8, and remember, delta S, entropy is in joules per Kelvin mole. So products minus, our reactant is 70.1 joules per Kelvin mole. So let's do that math. 188.8 minus 70.1. We have positive 118.7. This is joules per Kelvin mole. Let's change that to kilojoules. We need similar units when we're dividing, so that's just going to move it back 3 spots. So 0.1187 kilojoules per Kelvin mole. Now we can take this and we can plug in, now that we know delta H and delta S, we can plug it into our equation right here. So let's do our T. Our temperature in Kelvin is going to be 45.01 kilojoules over 0.1187 kilojoules per Kelvin. So let's do 45.01 divided by 0.1187. And we get 379.19 Kelvin. But when we talk about boiling point of water, we usually use Celsius. So let's put it into Celsius. We're just going to subtract 273.15. And so let's do that. Minus 273.15. We get 106.04 degrees Celsius is our boiling point of water. We know that boiling points are pressure dependent. So depending on where you're located, and I mean, we say that water boils at 100 degrees, but that's a standard pressure. So depending on where you are, that boiling point can fluctuate a little bit. So here we just found out that this water's boiling point is 106.04 degrees Celsius. So let's look at free energy and equilibrium. Free energy can be viewed as a measure of a process driving force. Okay, so if delta G is less than 0, so that means it's negative. That means that it is spontaneous in the forward direction. If delta G is greater than 0, so if delta G is positive, that means greater than 0, the driving force is pushing towards the reverse direction. So if delta G is greater than 0, so it's positive, the driving force is pushing towards the reverse direction. And if delta G is 0, the process is occurring in both directions at the same rate. So the free energy change for a process taking place under non-standard conditions are related to the free energy change by this equation. So we've been talking about standard state conditions, and we know that standard state conditions are under 1 atmosphere of pressure, 298 Kelvin, 1 molar solution concentration. So this is under standard state conditions. But what if it's not standard conditions? What if we're not under these ideal situations? So we're able to find that this just regular delta G is for non-standard conditions. And then to do that, we take our standard delta G, and this is our standard condition delta G, plus Rn natural log of Q. Now what does that mean? Here we go. All right. I feel like I said in this last one that we multiply, but we add. We're taking that standard state, flipping back here, and we add Rn natural log of Q. So most of our discussion of free energy to this point has involved the standard free energy change, delta G naught. And again, that's at 1 bar or 1 atmospheric pressure, 1 molar concentration, and this is going to help us get to that non-standard conditions. So where does this R come from? Do you remember back in Gen Chem 1 where we learned PV equals nRT? This was the ideal gas law. Oop, I don't want to point to N, I want to point to R. This is our ideal gas law constant. That R. And that R is 8.31 joules per Kelvin mole. But in this situation, since we have been using kilojoules for all of our delta G equations, we're going to move this back 3 spots. So this is where the R 0.008314 comes from. It's our ideal gas law constant plugging into R. Our T is the temperature in Kelvin at which this non-standard reaction is happening at, since we're not at 298 Kelvin. And then we're going to take the natural log of Q. And Q is the reaction quotient. So we're going to get into what that means next. Okay, so a reaction quotient. This is a concept that's really going to get hammered home in the next several units. But in order to find delta G at non-standard conditions, we have to know the reaction quotient. So we are really, the next few slides, we're really kind of foreshadowing what we're doing in the next couple of units. So we derive a reaction quotient directly from the stoichiometry of the balanced equation. So let's say that we've got A plus B reacts in dynamic equilibrium with C and D. And these little guys are the stoichiometric balanced coefficients for that problem. So a reaction quotient is written as simply, if we're looking at the concentration of that, we just do products over reactants, and we take our products, C times D, and they're raised to the power of whatever that coefficient is. So C to the, that is a silly X. C to the X, D to the Y, over A to the M, and B to the N. If we're looking at the pressure, let's say that all of our values were not in molarity, like concentration is, but in atmospheres, then I just find the pressure of C to the X exponent times the pressure of D to the Y over, it's still the same thing, products over reactants. Just here we're dealing with these brackets that signifies molarity, and here we're just looking at pressure. And we still raise, so this pressure of C to the X, pressure of D to the Y, pressure of A to the M power, pressure of B to the N power. So let's look at this again. Our QC is concentration, and that's in molarity, and it uses brackets. QP is the reaction quotient referring to pressure. And when we're writing this reaction quotients, again, we use these brackets because it's molarity. And here we do like the partial pressure of A raised to the m power, whatever that coefficient is. So let's practice writing and figuring out what the reaction quotient expression would be for each of the following. So we've got our products of a reactant. So we've got O3, so the concentration of O3 to the second power over the concentration of O2 to the third power. Notice that the second power, that means it's squared. The third power means it's cubed. Just products over reactants. So this is for letter A. Let's look at letter B. And this would be my reaction quotient as far as concentration. Let's do letter B. It doesn't tell us if we're given concentration or pressure, so let's do it both ways. So our QC is going to be products, so NH3 to the second power, that's my products, over reactants. I've got two reactants. I've got N2, so the concentration of N2, there's a 1 in front of there, so I just don't even need to write 1, times the concentration of H2 cubed. That's my concentration. What if I had partial pressures? Then I would say QP, my reaction quotient to find pressures, would be the pressure of NH3, whatever that value is, to the second power, right? NH3 to the second power, over the pressure given to me of N2, again, it's to the 1 power, times the pressure of H2 to the third power. Notice these look very similar. And then let's look at letter C. Let's do concentration for this one. So we've got products, we've got NO2, the concentration of NO2 to the 4th, times H2O to the 6th, over NH3 to the 4th, times O2 to the 7th. So I know that seems like a lot. And why are we doing this? Because we need this reaction quotient in order to find delta G at non-standard conditions. Once we know that reaction quotient, that value, then we can plug it in into our delta G at standard conditions plus RT, natural log of that reaction quotient. So let's look at an example problem. We need to calculate delta G under non-standard conditions. What's the free energy change for the process shown here under the specified conditions? So I've got NH3 gas decomposing into 3 H2s and N2. Now we're given the partial pressure information for N2, for H2, and for NH3. Okay, so first thing we're going to do, and remember this is at non-standard conditions. We are given delta G at standard. So we're going to use that equation, delta G is equal to delta G naught, that plus RT natural log of Q. So let's set up that reaction quotient. And since we're given all of our values in ATMs, we're going to set up our Q for pressure. And again, we're going to do products over reactants. So I'm going to do the pressure of H2 to the 3rd power times the pressure of N2 to the power of 1 over the pressure of NH3 squared. Now let's plug in our values. The pressure of H2 we were told was 0.250 atm, and that's going to be cubed, times the pressure of N2, 0.870 atm, all over NH3, 12.9 squared. Okay, so let's plug this into our calculator here. I'm going to do 0.250 to the third power and times that by 0.870. And then I'm going to divide it, I'm going to divide it by, I'm going to put in parentheses here, 12.9 squared. And I should get a reaction quotient of 8.17 times 10 to the negative 5. Okay, that's unitless. So this is our Q. Now let's plug it into our equation. We're going to do delta G at our non-standard state is equal to our delta G at standard state, which is 33.0 kilojoules per mole, plus R, remember we said R was 0.00831 kilojoules per Kelvin mole. The temperature, and we were told temperature up here was 25, so plus 273. So our temperature is 298 Kelvin times the natural log of 8.17 times 10 to the negative 5th. Okay, let's plug this in. I'm going to do this part all first. I'm going to do the natural log ln of 8.17 times 10 to the negative 5th. I'm going to times that by 298 and times that by 0.00831. Then I'm going to add 33 plus 33. And I got a delta G of 9.69 kilojoules per mole. Therefore, this is telling us that it's still non-spontaneous. Even at the non-standard conditions. It was really non-spontaneous before 33, but even despite the changing conditions, it's still not spontaneous. So if we were to go back and just replay the steps that we did to solve this problem, we were told that this was under non-standard conditions. We were told the conditions of pressure for these reactants and products. So when we said, okay, we need to find Gibbs's free energy at non-standard state, we're going to do delta G is equal to delta G, the standard state, Gibbs's free energy, plus RT, natural log of Q. So the number one thing we did was find that Q, the reaction quotient, using our pressure values. And we did products over reactants. Took our products and made sure that those coefficients were the exponents. We then plugged in the values that we were given for those products over reactants and found our Q. Then we plugged it into our delta G, non-standard state. Our Q, standard state, gives us free energy, plus R, which is our ideal gas law constant, R times the temperature given times that natural log of Q to find what our delta G is at non-standard states. Let's do another practice, another non-standard condition. So let's say for a gaseous reaction, the standard conditions are 298 Kelvin and a partial pressure of 1 atmosphere for all species. That's our standard conditions. Again, 1 atmosphere for all species. So here we have this reaction, nitrogen monoxide plus molecular oxygen creates NO2. But we can see here that we're given pressures that are not 1 atm. We've got 0.2, 0.3, and 0.7. We do know that the standard change in Gibbs's free energy for this reaction is negative 69.0 kilojoules per mole. What is the delta G for this reaction when the partial pressures are not at 1? So we know that we're going to use that equation, delta G at non-standard is equal to delta G standard plus R T natural log of Q. Okay, so step number 1, we need to find that reaction quotient. So let's do that first. Since we're given all of our values here in atmospheres, we're going to find that quotient, the pressure quotient. So again, we do products. So we're going to do the pressure of NO2 squared over, so products over reactants. So then we need the pressure of NO squared times the pressure of O2. And there's no exponent there because there's just a 1 there. So let's find our pressure of NO2, which is 0.7 atm. We're going to square that over pressure of NO, so 0.2 squared times the pressure of oxygen, which is 0.3. So let's do the math here on this calculator. I'm going to do 0.7 squared, and I'm going to divide that by 0.2 squared times 0.3, and then close that parenthesis. And I got a product or answer of 40.83. This is my Q, my reaction quotient. So now we just need to plug it in. Let's do our delta G is equal to, our standard G should be given to us, negative 69.0 kilojoules per mole, plus R we know is 0.00831 kilojoules per Kelvin mole, times temperature, it says 298 Kelvin, and then times the natural log of 40.83. So let's do some calculator work here. I'm going to do the natural log of 40.83 first. Times that by 298 and by 0.00831. And then add that to our Gibbs's free energy, which was negative 69. And we end up with a delta G of negative 59.8. So even under non-standard conditions, we still have a negative delta G, so it will still be spontaneous, despite not having those pressures at 1 atm.